afternoon, everybody. Sorry, getting a little bit of an echo there. So it's great to see all of you here today. I really like that introductory video. It's a little guilty pleasure of mine, and in these weird times, I think it can also help us to feel a little bit more normalcy in this weird routine that we've fallen into now that we're teaching remotely this semester. So can I get real quickly a check-in on everybody? Can everybody hear me? If you can hear me, go put up your hand in the Zoom chat if you're participating with us live, just so that I know. Okay, we got a hand. I'll take the one hand. Thank you. So let's get going here today. I actually need to turn off my phone because it doesn't know how to be quiet. There we go. I think I got it. Cool. So today, the plan for our next little bit of time together is I'd like to clean up the trigonometry topics that we didn't get to in our last session. So that's going to include sort of two sections that correspond to two objectives in our syllabus. Let's actually start real quickly here by taking a look at the syllabus together, just so that I can point at the things that I wanted to point at. So here's a copy of our syllabus for the semester. And so we are working today on the topics that are right here in the trigonometry workshop. So topic T3 on right triangles and tangents, as well as T4 on inverse trigonometry. In our textbook, that's section 4.2 called the tangent function, as well as 4.3, which is inverses of trigonometric functions. So what I thought I would do today is sort of get us started with the preview activities. So most of you have submitted some preview activities for these two sections, but I think it would be a good idea if we sort of just took a moment and worked through those activities together. I put these videos into our YouTube playlist for the course, but I'm going to broadcast them here during class. They're only, each one is like 10 minutes or so-ish long. So let's look at these together. I'll take some questions, then we'll launch into the rest of the activities in these sections. So first off is the preview for section 4.2. And 4.2 is where we get introduced to the tangent function. So at this point in the semester, we know about sine, we know about cosine, we know how they work in right triangles, we know how they work on the unit circle. And so what is tangent? It's the third of our big three trigonometric functions. What is it? How do we understand it in several different ways? And how can we use it to help solve some applied problems? So that's the first thing we're going to look at through this first preview video for today. So now that we know about sines and cosines in trigonometry, it's time to talk tangent. In this video, we'll get an introduction to the tangent function, the ways to think about how to understand a tangent, and then also some of the properties that the function f of x equals tangent of x enjoys. So first of all, how do I compute the values of selected tangents of certain angles? So let's think about tangent in these three different ways. On the one hand, So now that we know about sines and cosines in trigonometry, it's time to talk tangent. In this video, we'll get an introduction to the tangent function, the ways to think about how to understand a tangent, and then also some of the properties that the function f of x equals tangent of x enjoys. So first of all, how do I compute the values of selected tangents of certain angles? So let's think about tangent in these three different ways. On the one hand, we can think of the tangent of an angle as the ratio in a right triangle between the opposite side All right, everybody hear me again? I think we worked through all of our issues. So that was our introduction to what tangent is. And probably most important piece of that introduction was sort of the three different ways of thinking about tangent. I'm just going to bring those, let's see. I'm going to try and bring that back on the screen for just a second so that we can, I just want to point at them briefly. Where did they go? Here we go. And I'll just flip over to the browser. There we go. So the three ways of thinking about what tangent mean are, on the one hand, the right triangle definition, where we think of it as what we get when we divide the opposite side in that triangle by the length of the adjacent side to that angle in the triangle. But maybe the most powerful way to think about what tangent is tangent is just a slope, right? When I take the tangent of an angle, x, I'm measuring the slope of the line, which makes an angle of x with the positive x-axis. Those two definitions are really, I think, the most rich and fruitful, and of course the one that's most largely applicable and the one that most trigonometry students remember coming out of a trig class is that tangent is nothing more than sine over cosine. This is the definition that's going to help us to use tangent when we do algebra and not just when we do geometry and other sort of visual types of problems. Does anyone that's watching right now on Zoom have questions or things you want me to clarify about tangent before we go forward and start working some problems that use tangent to help us to solve some geometry questions? Hopefully in the process of working some of these questions, some of these problems, those questions might be addressed in some way. So the remaining activities that are in this section are both kind of apply problem solving flavored. And so they're going to, we're going to use our sort of geometric intuition of tangent to help to solve them. Let's take a look at this first one. In this first question, they tell us that there's a 225-foot tower. Maybe it's a radio tower or something. It's anchored to the ground by cables that make an angle of 32.5 degrees with the ground. And they want to know how long do we need to make the cables and how far from the base of the tower do we need to anchor those cables. So step one in any problem like this that has a geometry flavor to it, try and draw a useful picture. So here's my radio tower. And I know, for example, how tall my radio tower is. I'm going to attach this red cable to it to anchor the tower to the ground some distance away. And so I'll put in the information that I know. The tower is 225 feet tall. The angle that the anchoring cable makes with the ground is 32.5 degrees. And so what are we being asked for in this problem? We're being asked how long the cable has to be. And so in my diagram, that's the length of this red line right here, line segment. It's the hypotenuse of this right triangle. I'm going to call it capital L. So if I want to know how long the cable has to be, I'm going to be solving for L. And then also we want to know how far from the base of the tower the cable needs to be anchored. And so the anchor point is this point over here in the end. So how far from the base of the tower does that anchor point have to be? I'm going to call that X, and that's going to be the other one of my unknowns. One of the things that you notice in this problem, if you take the usual approach of, well, what do I know and what am I trying to find? If I only look at the lengths of the sides of this triangle, I don't have enough information. For example, if I just try and use the Pythagorean theorem, x squared plus 225 squared is going to be equal to L squared. And the problem with that is that I don't know x and I don't know L. So I can't just rely on the Pythagorean theorem to be able to solve for the two missing lengths of this triangle. That's not enough information. So I'm going to need to somehow use this angle measurement, 32.5 degrees. This is going to have to be a piece of the puzzle. So what I like to recommend doing anytime you're trying to solve a right triangle is to try and write down all of the trigonometric ratios that you know. Sine, cosine, and tangent. And using the old mnemonic, the old SOHCAHTOA mnemonic, remember that the sine is the length of the opposite side of an angle divided by the length of the hypotenuse. The cosine is the length of the adjacent side divided by the length of the hypotenuse. And the tangent, as we were just talking about in the introductory video, is the ratio of those two. And for that reason, it's the length of the opposite side divided by the length of the adjacent side. So let's take the only angle that we happen to know in this problem, or at least the only angle in the triangle that's going to be helpful, because we know the 90-degree angle in this right triangle, but that's never going to be useful for the purposes of computing sine, cosine, or tangent of something else. The only angle we know is this 32.5 degrees. So we'll ask what ratio the sine of 32.5 degrees is going to represent in this triangle, what ratio the cosine represents, and what ratio the tangent represents. And so then we'll ask the question, with respect to this 32.5 degree angle, which side is opposite, which side is adjacent, which side is hypotenuse? So the opposite side to this 32.5 degree angle, we go all the way across the triangle here and find the opposite side is my 225 degree height of my tower. So I'll put that 225 in place of all of my opposite sides. So we're getting there. The adjacent side, this is a side that's not the hypotenuse, but which is a part of my angle that makes up my 32.5 degree angle. And so that adjacent side is what I'm calling x. It's how far from the base of the tower this cable has to be anchored. Excuse me. And so in place of adjacent, I'm just going to write x, x here, x there. And then finally, the hypotenuse of my triangle is the length of my cable. It's what we're calling L here. So in place of the hypotenuse, I'm just going to write L. So I like this little strategy because this helps us to kind of focus in on which one of these trigonometric ratios is going to help us to solve each one of the problems that we're working on. Keeping in mind that the left-hand sides of each one of these equations, these left-hand sides are just numbers. The sine of 32.5 degrees, that's a number. The cosine of 32.5 degrees is a number. And so the only unknowns that we have in here are, respectively, L and X. Right? And so we want to focus in on the equations that only have one unknown in them. So those are going to be the ones that we'll be able to solve for our unknown as a numerical answer. So here, the first example and the last example. So I can use the sine of this angle, 32.5 degrees, to solve for the length that I need for my cable. I can solve this for L. And I can use the tangent of 32.5 degrees to solve for x, how far away my anchor has to be from the base of the radio tower. And for the cosine, let's just kind of forget about it, because it's going to have both of my unknowns in it. It's probably not going to be as directly useful. So let's take a moment and just algebraically solve these two equations for their unknown. I'm going to open up a little graspable math window here to just take us through those steps. So I've got the equation, the sine of 32.5 degrees is equal to 225 over L. And so our job, and let me switch over into my browser view here real quick. There we go. So our job is going to be to try to solve this equation for L. Well, how am I going to do that? I need to get this L by itself. What I like to do in those cases is just flip this fraction upside down. So take this L, move it upstairs, and the 225 then moves downstairs. And yet again, having trouble getting this thing to do what I want it to do. Let me undo that for just a second. If I move this 225 down, I can move this L up. And if I do that, then I can do it on the other side of the equation as well. Probably the way they want me to do this is multiply both sides by L, divide both sides by 225. Uh-oh. Divide both sides by 225. It's not letting me do that. Trust me, that's an okay thing to do. And then divide both sides by the sine of 32.5. So this is where I actually wanted to come out of this, right? If I solve this equation for L, this is what I get. 225 over the sine of 32.5. Well, remember, this angle here, 32.5, is being measured in degrees. So if I put that back into my problem here, L is going to equal 225 divided by the sine of 32.5 degrees. I'm going to need to evaluate this numerically. And to evaluate that numerically, I'm going to need to pull out a calculator, and that calculator needs to be in degrees mode. So every calculator that does scientific functions will give you the ability to put your answer into degrees. So just as an example, let me switch back to my video here for just a second. So here I have just a generic scientific calculator, and it has a little button that says degrees, D-E-G, on it. You can kind of see right up there, kind of in the middle, right? So if I change the calculator into degrees mode, and then I take 32.5, and I take the sine of it, let's see. Why don't I do this? Let me see if I can get a Desmos window to do this. 32.5 degrees. Whoops. Let's see. Ah, there we go. So maybe here's a better way to do this. Let me switch over to a Desmos window. We'll do this with our Desmos online graphing calculator. Here we are. So notice that the default in Desmos, if I try to evaluate a trigonometric function, it's going to think about this angle as being measured in radians. So if I want to change that, what I'll do is go up into the options menu, the graph settings menu, click on that. It gives me the option here at the bottom to select whether trigonometry is done in radians or it's done in degrees. Again, most of the time we're going to do everything in radians in this course, but because this problem gave us an angle in degrees, we'll use degrees mode to actually do this. So the sine of 32.5 in degrees is about 0.5373. So we'll put that as the denominator, 5373. Let me switch back into our work here. So sine of 32.5 degrees is 0.5373. And so when I divide 225 divided by 0.5373, I'm going to get my answer, which is about 418.76. 418.76. And again, the units on that, because this 225 is measured in feet, and the denominator is the sine of something, that denominator is dimensionless. When I divide feet by something which is dimensionless, my answer is going to end up being measured in feet. And so we have figured out now how long this cable needs to be. 418.76 feet. So that's how long we need our cable to be. We use the sine to get that, and the reason that the sine was helpful is that the sine relates the opposite side of my triangle, which I know, to the hypotenuse, which I didn't know, but I knew the angle, and so I knew what the sine of 32.5 degrees was. And so that was enough information to let me solve for this hypotenuse. Same story is going to let me then solve for the unknown other base of this triangle, how far away my anchor point needs to be from the base of the tower. So to get that, I'll use this equation that we devised here. The tangent is going to be what helps here. Because I happen to know this angle, I know the opposite side, and the adjacent side is the thing that I don't know. Right? So since the tangent relates opposite and adjacent, I'll be able to use the tangent to figure out the measure of that missing side. So let's do that piece. So we'll take that equation, tangent of 32.5 degrees is equal to, I'm going to type in here, tangent of 32.5 degrees is equal to 225 over x. And we're going to try and then solve that equation for x. So let me switch over again into our palette. So same strategy. If I want to get that x by itself, the first thing I might do is multiply both sides by x. And after I've multiplied both sides by x, I can then divide both sides by the tangent of 32.5. And there I've rearranged this equation to get the x by itself. So it looks an awful lot like the expression that we had to solve for L. It's just in place of the sine, which is what helped us to solve for L, now we've got the tangent, which is going to help us to solve for x. X is 225 divided by the tangent of 32.5 degrees. So, to compute the tangent of 32.5 degrees, we'll do the same story. We'll just open up a graphing calculator, make sure that it's set in degrees mode, and then ask what is the tangent of 32.5. Remember, this is going to be the same thing as the slope of a line which makes a 32.5 degree angle with the positive x-axis. So the way that I've drawn this diagram makes it look like that slope would be negative, except look where we're measuring from. We're measuring from an x-axis here that sort of is the negative x-axis instead of the positive x-axis. So another way to think about this in the slope viewpoint is to take that 32.5 degree angle and just imagine that it's an angle of inclination here to the positive x-axis. Right. Sorry, that diagram didn't look great. Let's try that one more time. Okay. So here's my 32.5 degree angle, and so then this slope is going to equal the tangent of 32.5 degrees. And so we expect that this tangent is going to be a positive number because that line that I've drawn here has a positive slope. And sure enough, when I ask a calculator what is the tangent of 32.5 degrees, remembering that we have to be in degrees mode for this, I get the positive number that's approximately 0.637. And so that'll be the denominator, 0.637. That I'll divide 225 over that. And getting out my arithmetic machine, 225 divided by 0.637 gives me about 353.22. I'm just rounding that off a little bit. 353.22. Again, that's going to be measured in feet because my 225 was measured in feet, and the tangent of 0.637, because it's a trigonometric ratio, is dimensionless. So at the end of the day, I need to anchor this cable about 353 feet away from the base of the tower. So there's an example of how we would use the tangent function to help us to solve applied problems, right? Because the tangent relates the opposite side to the adjacent side in a right triangle, it lets me, if I know the angle to which they're opposite and adjacent, I can use the opposite side to solve for the adjacent side, which is what we did here, or conceivably we could have also done the opposite. If I knew how far away the cable was tethered and I knew this angle, it would let me solve for the height, the opposite side. Does anyone watching on Zoom have questions or things that they want to clarify before we turn the page and start talking about inverse trigonometry today? Cool. Let's talk inverse trig. So just like with our introduction to tangents today, I've got an introductory video that's a part of our YouTube playlist that I want to use to kind of get us started. So I think I've worked through all of the technical challenges that we had with that before. It should allow us to watch this together real quick in Zoom. And then from there, we'll use that as the jumping off point to a couple more activities using inverse trigonometry. So let me switch over into our video here. I'll hide my second head. And then we will, hold on, let me fix the Zoom feed. Simulcasting is hard. We'll switch over to here. Okay, I think we're in good shape. I'm just going to start this video, and then when we come back, we'll go from there. With everything that we know. We can ask the question, do these functions also have inverse functions? In other words, is there a function that can undo what, for example, cosine does? So if you were to give me an angle, and I were to tell you the cosine of that angle, could we play that game in reverse? Could you tell me the cosine of an angle, and I would figure out what that angle actually was? Doing so would mean that we can define an inverse for the cosine function. That's going to be what this introductory activity kind of walks us through a little bit. So what we're seeing here is the graph in the dotted line here of the function f of x equals the cosine of x. And a portion of it has been highlighted, just the portion with the domain from t equals 0 to t equals pi. And just this little portion, this little highlighted portion here, is what we're going to call the function g. So this is y equals g of t. It's the portion of the cosine function which has the domain of just t ranging from 0 to pi. So what is the domain of this function? The domain of this function is the portion of the horizontal axis that this graph covers. It's just t ranging from 0 to pi, inclusive of both, so we're including both of the endpoints. T equals 0 is a part of the domain. T equals pi is a part of the domain. So we could write this in interval notation if we wanted to as 0 to pi with square brackets on both ends to include each of those endpoints. So that's what the domain of this function is. And keep in mind, when we restrict the domain, we're totally ignoring the rest of the cosine graph that we otherwise would have seen here. So we're only thinking about this piece of the graph right now, because the only thing my function sees are the t-values between 0 and pi. We'll see why that's important in just a second. What's the range of this function? That's what we get if we take the graph and we squish the graph onto the vertical axis, the y-axis, and ask how much of the y-axis is covered. How many different values can y equals g of t, where g is the cosine function on 0 to pi, how many different real number outputs can we get? If we squish that graph onto the vertical axis, that graph covers every real number from -1 on the bottom to +1 on the top, inclusive of both. Because after all, the cosine of 0 is equal to 1, and 0 is a part of my domain. And the cosine of pi is -1, and pi is also a part of my domain. So that means -1 and +1 should be included in my range because they arise as outputs of my function when the domain is from 0 to pi, inclusive of both. So in an inequality, we could write the range of this function as the g of t values that range from -1 to +1, inclusive of both. And in integral notation, we'd write it as -1, 1, with again square brackets on both ends because we can include both -1 and +1 as outputs. Okay, so now we can take this a step or two further and ask if this is the function that we're wanting to think about here, and this function is, just a piece of the cosine graph. Does this function have an inverse function? That's where we want to ultimately go here. So the first question you always want to ask when you're asking about inverses is, does my graph pass the horizontal line test? Is my function one-to-one? Or is it possible that two different inputs to my function could give me the same output? Because if that's true, then to undo that process would give me something which would no longer be a function. And so in order for a function to have an inverse, it needs to be one-to-one. Different inputs have to give me different outputs. And the horizontal line test is how we check that on a graph. So does my graph pass the horizontal line test? It absolutely does. Because remember, we're just thinking about this one blue piece of the curve right here. And any horizontal line that I can draw is only going to intersect that blue piece of curve at most one time. It never intersects it more than once. So does this graph pass the horizontal line test? Yes, it does. But now keep in mind that that was only the case because we forgot about some of the graph of the cosine function. Remember, we restricted the domain. The cosine function, if its domain is considered to be all real numbers, all real angles, would not pass the horizontal line test. Because any line that crosses the cosine graph once, any horizontal line that crosses it once, is going to cross it, in fact, infinitely many different times, unless we restrict the domain. So in order for us to pass the horizontal line test, we have to have restricted the domain of our function. So if we do restrict the domain, and we do get an inverse function for cosine, what are some of the properties of that inverse function? So what would the domain and the range of the inverse of the cosine function be? We can figure that out by thinking about what the graph of the inverse function of cosine would look like. Remember, the graph of the inverse of a function is nothing more than what we get if we reflect the original graph over the diagonal line y equals x. That corresponds to an interchange of the input with the output, which after all, that's exactly how we define inverse function. If I reflect this graph, I'm going to get a graph that looks something like this, right? Where my original cosine graph had the point pi -1, my inverse cosine graph is going to have the point -1 comma pi. Reverse the x with the y. 0, 1 became 1, 0, and pi over 2 comma 0 became 0 comma pi over 2, right? So all my x's became y's, all my y's became x's. This is what happens when we pass to the inverse of a function. Everything is backwards. And so, what are the domain and the range? Well, since the domain of a function specifies all of its input values, its inverse function would have those input values as output values instead, and vice versa. The range specifies all the output values of a function, and those outputs are going to be inputs of the inverse. Therefore, the domain of the inverse is the same as the range of the original function, and the range of the inverse is the same as the domain of the original function. So the domain of the inverse cosine is the range of the original cosine. So the domain is going to be -1 to 1. And the range of the inverse cosine is the domain of the original, which again, we had to restrict the domain of the cosine in order to get it to have an inverse, and the way we restricted it was to look at just from 0 to pi. So that becomes the range of the inverse cosine. So to wrap this up, let's think about what the inverse cosine function could tell me. Here's an example from the unit circle. So in this example from the unit circle, I can take any angle that I want to on my unit circle, And I can see how that angle on the unit circle corresponds to a point on the graph of the cosine function. So let's go back to a right triangle that we know very well, a right triangle that makes an angle of 60 degrees with the positive x-axis. That right triangle is showing me that it had the cosine of 60 degrees is the horizontal coordinate, 0.5. That also corresponds to this point, 60 degrees, 0.5 on the graph of the cosine function. So what does this tell me about the inverse cosine? It tells me that the inverse cosine will take the number 0.5, 1/2, and return the angle, 60 degrees. So the inverse cosine of 0.5 is 60 degrees, because the cosine of 60 degrees is 0.5. Remember, the inverse cosine does exactly the opposite of what the original cosine does. And then just to finish that point, because the cosine of pi over 3 is 1/2, the arc cosine should do the opposite thing. Arc cosine of 1/2 is pi over 3. And this is a decimal approximation for pi over 3. You can check that that's actually what this is. And again, that's because the point pi over 3, 1/2 is on the graph of the cosine function. And therefore, when I flip this graph over the line y equals x, the corresponding point on the graph of the inverse function is 1/2, pi over 3. So the inverse cosine of 1/2 is pi over 3. Last thing I want to mention is the name that we give to the inverse trigonometric functions. We give them the name arc. So arc cosine is the inverse function of cosine. Arc sine is the inverse function of sine. And arc tangent is the inverse function of tangent. Those are the only names and notations I'm going to use for inverse functions in trig. Make sure you don't get confused by other notations that get used out there that use an exponent of -1. Strike those from your memory because they can confuse you more than illuminate you. I will always call them arc functions. Arc sine, arc cosine, arc tangent. Those mean the inverse function of sine, inverse function of cosine, inverse function of tangent. All right, so hopefully we are back. Yes, I think we're in good shape. Let me click this button right here, and I think we're back to where we need to be. So, as you might expect, having inverse functions to sine, cosine, and tangent are ultimately going to let us solve equations where the unknown is on the inside of one of those functions. So if I can undo a cosine function, I can solve an equation where my variable x maybe is inside a cosine function. If I can undo the tangent, then anytime my unknown is trapped inside of a tangent, I can use the arctangent to unwrap it, right? And so this is our first introduction to the functions that have the power to do that, to undo a sine, to undo a cosine, to undo a tangent. So I want to start by doing just these few just a few of these examples from the next activity in the section, which are just invitations basically for us to evaluate some arc functions. So I'm going to zoom in on this real quick. Let's take this first one up here, the arc cosine of the square root of 2 over 2. So for that, I'm going to come back to this little diagram that I used in the introductory video here. This was produced by somebody named Anthony Orr on GeoGebra. I think it's a really nice little visualization for how all this works. So if I want to know what is the arc cosine of the square root of 2 over 2, then what I want to do is I want to, in this diagram, figure out how to get a horizontal coordinate on my unit circle of square root of 2 over 2, which is about 0.7071. So I need to make that purple coordinate there equal to square root of 2 over 2. And there it is, actually. Let me maybe zoom in on that just a little bit more, just so it's as legible as possible, and then I'll put it back to where it was. So here on my unit circle, if I'm asking for the arc cosine of 0.707, I'm asking for an angle whose cosine, horizontal coordinate, is equal to 0.707, right? Square root of 2 over 2. So remember, that's the job of an arc cosine. It takes a horizontal coordinate as the input, and it spits out as the output the angle that has that horizontal coordinate as its cosine. That's, after all, what inverse functions always do. They undo whatever the original function did. Okay. So the arc cosine of the square root of 2 over 2 is, and I'm going to read that in English the way that we just said it. It's an angle, it's an answer to the question, what angle has a cosine of square root of 2 over 2. Right? And according to what we know about our unit circle trigonometry, the answer to that riddle is that that angle is 45 degrees, or better yet, pi over 4 radians. So the arc cosine of the square root of 2 over 2 is pi over 4. Why? Because, again, just to really hammer home this point, because the cosine of pi over 4 is the square root of 2 over 2. Right? So those two equations have equal truth value, right? And that's what we mean when we say that the arc cosine is the inverse function to the cosine. Whatever input we give to the cosine becomes the output that we get from the arc cosine, and vice versa. The output from the cosine is the input to the arc cosine. Right? It just reverses the same relationship, reverses the roles of input and output. Let's move forward to the next example, but I kind of want to, well, okay, we'll do this next example the way that it is, and then maybe we'll tweak it a little bit. Arc cosine of negative 1/2 is going to be an answer to the question, what angle has a cosine equal to negative 1/2? Okay. And so what we need now is we need for my horizontal coordinate to be negative 0.5. So I just need to find a way of moving my angle around the unit circle until my horizontal coordinate is negative 0.5. And here it is, right? And at least according to my the applet that I'm using here in GeoGebra, that angle is a 120 degree angle. And so the arc cosine of negative 1/2, an angle whose cosine is equal to negative 1/2, is 120 degrees. Or better yet, since we don't like using degrees very much, we'll convert that into radians. It's 2 pi over 3 radians. The arc cosine of negative 1/2 is 2 pi over 3, exactly because the cosine of 2 pi over 3 is negative 1/2. And that's all there is to that, right? Before we go into a couple of the more interesting examples on this section, what I'd like to do is actually modify part C. So just so that we get a chance to get a little practice with another arc function. What if part C were asking for the arc sine instead of the arc cosine for the square root of 3 over 2? Let's do that piece. So for that, I need a sine graph instead of a cosine graph. Oops, hold on, let me reload this page because my zoom is getting all thrown off here. Okay. So for this, the arc sine of the square root of 3 over 2 is an answer to the question, sine of what angle is equal to the square root of 3 over 2? So whatever fills this output from the arc sine function is what filled the input to this sine function. So for this, I'm going to be looking on my unit circle for a point whose sine, remember sine is the vertical coordinate of the unit circle, I want the vertical coordinate to be the square root of 3 over 2, which is about 0.866. So I'm just going to move my angle around here until I get something that has a vertical coordinate of 0.866. Oh, there it is, right? And so here on the unit circle, the vertical coordinate is the square root of 3 over 2. And therefore the sine of this angle, 60 degrees, is equal to this vertical coordinate on the unit circle, square root of 3 over 2. The sine of 60 degrees is the square root of 3 over 2. And for that reason, the arc sine of the square root of 3 over 2 is 60 degrees. Or, as we alternately know it, pi over 3 radians. So there's an example of an evaluation for the arc sine. I want to do one more quick example before we wrap up this this portion of what we're doing, and we'll wrap up our session for the day. And the last example that I want to tackle is kind of a compound example. It's the one that I wrote down here, this part K. Suppose we're asking for the sine of the arc cosine of the square root of 3 over 2. How about I think about this problem? So how I want to think about it is I want to start by using the order of operations, right? And what that means is to evaluate the expression that's on the inside of the innermost parentheses first. So let's focus first on the arc cosine of the square root of 3 over 2. How do we understand the arc cosine of the square root of 3 over 2? It's an angle whose cosine is equal to the square root of 3 over 2. So, just as we did before, we can use our knowledge of the unit circle to answer that question. So if I want an angle whose cosine is the square root of 3 over 2, I'm going to change this angle here until I get 0.866, that's square root of 3 over 2, as the horizontal coordinate. That corresponds to an angle of 30 degrees. 30 degrees is otherwise known as pi over 6 radians. So if we go back to where we were, we could replace the arc cosine of square root of 3 over 2 by pi over 6 radians. And then we would just be forced with the evaluation of the sine of pi over 6, and we know what the sine of pi over 6 is. It's 1/2. But I think that is a pretty unenlightening way to do this problem. I would rather do this problem in a slightly different way. Let's see if we can do it without following the algebraic path, but let's try to follow a geometric path instead. And to do that, I'm going to focus on this observation. Whatever the arc cosine of the square root of 3 over 2 is, let's give it a name. Let's call this thing x. It's the answer to the riddle, cosine of x is equal to square root of 3 over 2. But since we know a lot about right triangles and how trigonometry works in right triangles, here's an option that I think is an easier option to take and helps ground us in the concepts of right triangle trigonometry instead of kind of blindly following an algebraic procedure, which always gets us into trouble, right? So let's imagine that I have this fictitious right triangle and that I have the angle x inside of my fictitious right triangle. I don't know what x is. I'm going to pretend I don't know what x is. But I do know what the cosine of x is. It's the square root of 3 over 2. And for that reason, we can interpret this ratio, square root of 3 over 2. I can interpret this as the ratio of the cosine, which is adjacent over hypotenuse. Remember, that's what cosine is. It's the adjacent side divided by the hypotenuse in a right triangle. And so what that lets me do is I can label this fictitious right triangle. I can label its adjacent side to have the length square root of 3 over 2, and the hypotenuse to have the length 2. And if I do that, then the angle that I get down here, x, is going to be exactly the angle that has a cosine of square root of 3 over 2. So that's my little nifty, one weird trick for this kind of problem. I'm just going to label my adjacent side, and adjacent is this side down here on the bottom, right? I'm going to label that adjacent side as having a length of square root of 3. And then I'm going to label my hypotenuse of my triangle, the denominator in my cosine. I'm going to label that hypotenuse as being a length of 2. So in my triangle, I'm going to have 2. Right? So now I have a right triangle, and I have an angle in that right triangle whose measure is exactly equal to the arc cosine of the square root of 3 over 2. So what is my question asking me to do? It's asking me to find the sine of that angle, whatever that angle happens to be. I don't even need to know that it's pi over 6 radians or whatever, right? I just need to know, what is the sine of x? Well, what's the sine of x when x is in a right triangle? It's the opposite over the hypotenuse. And we happen to know that the hypotenuse is 2, so we'll just put that 2 in there. And that just leaves us with the question, what is the length of this opposite side? If I call that opposite side something, let's call it, I don't know, A, right? Then A is the length of this side in my right triangle. How do I find the length of that missing side? Well, I know the lengths of the other two sides. So I can use the Pythagorean theorem to discover the missing third length. A squared plus the square root of 3 squared is going to be equal to 2 squared. And when I solve that equation for A, I'm going to discover that missing length. Square root of 3 squared is otherwise known as 3. 2 squared is otherwise known as 4. And so I get this nice little equation, A squared plus 3 is equal to 4. That's not the hardest thing in the world. I'll subtract 3 from both sides to get A squared is equal to 1. I'll take the square root on both sides to discover that A is going to be equal to plus or minus the square root of 1. Well, but A is the length of the side on a Euclidean triangle, so we're just going to take the positive answer. A is equal to 1. And that allows me to finish my answer. Magic. So this, by the way, is a really useful trick later on in calculus. One of the things that you end up doing, particularly in second semester calculus, when you have to do calculus with trigonometric and inverse trigonometric functions, These are really sort of multi-tools for helping us do calculus, and you end up with having to confront some expressions that look kind of like this, with a little bit of regularity in your second semester of calculus. And the easiest way to understand and do bookkeeping on all of your trigonometry and your trigonometric functions is to just construct a triangle that has the properties that we're looking for. In this example, I constructed a triangle that has an angle x in it, whose cosine is the square root of 3 over 2. That angle is, by definition, the arc cosine of the square root of 3 over 2. And if I then need to know what the sine of that angle is, I can use what I know about right triangle trigonometry. That's SOHCAHTOA working for you. So that'll wrap us up for this week's material, and that wraps up the trigonometry content going into our next exam. So if you're currently my student and you're working on some stuff, what you want to be focusing on right now are the web work problems that are associated with this material. Be on the lookout in Canvas for some quizzes to come up shortly. We're going to take the next week and a half or so to focus first on doing those quizzes, getting some feedback on those quizzes. I'm going to be using our live sessions, our live virtual sessions, to just do some problem solving. So be in communication with me between now and our next sessions on Monday and Wednesday as you're working through the quizzes, as you're working through the homework. If you have questions you want to see me address, that's what I want to use those sessions to do. And then once we have done those quizzes and gotten feedback on those quizzes, that's when I'll make the exam on this material available as well. So I look forward to working on the rest of this with you as we go forward over the next couple of weeks.